My name is John Handshoe, and I'm a science teacher at Hazard Independent Schools. This year, one of our projects has been sort of a pet project of mine over the last couple years, and it's something, the technology is something called a metal air battery. Any of you all ever heard of that before? You probably will be in the next few years. It's a different type of battery. To tell you a little bit about it, most batteries, when you hook a load up to a battery, you have an electrical current. You have a flow of electrons basically coming from a chemical reaction that's going on with two metals and an electrolytic solution in the middle, which basically that just means it's something that will conduct electricity. So you get this flow of electrons from one side of the battery to the other. An aluminum air battery has been out probably the last 20, 30, 40 years, but we haven't seen a whole lot of it until recently. But the difference with an aluminum air battery is the electrons, instead of basically coming from the electrolytic solution, come from the metal itself, the aluminum. And it reacts, instead of a different metal, the aluminum air battery reacts with oxygen in the air. So what happens here is when you fire up one of these cells or these batteries, you have the aluminum basically giving up electrons. So the process goes real quick, but some of the advantages to an aluminum air battery is that you have something, there's a term in here called energy density. And what that means is, with energy density, it's basically how much punch the battery packs, how much stored energy it has. They estimate an aluminum air, and I say aluminum air, you can also use other metals in this same technology. But they estimate that aluminum air batteries will produce somewhere between 5 and 10 times more quantity of electricity than standard alkali chemical batteries, even lithium-ion batteries. In addition to that, because of your anode and cathode, the aluminum is an extremely light metal, and in order to collect the air for the other electrode, basically you have to have some material that works just to collect air. And those two things, the aluminum and the air, generate the electricity. If you get back home, you can do a quick YouTube search on it and basically make a battery in 5 minutes out of salt water, aluminum, and some charcoal. That'll generate somewhere between 0.6 and 1.5 volts, a cell actually. But so one of the advantages of these batteries is that they're extremely light. They have this huge power output. We estimate, for our purposes, we estimate them to have about 8 times the energy density of another battery. So one of the first questions we always get asked as we're working on this is, what in the world is preventing us from using these batteries right now in real life, out there in the real world? They have a couple of drawbacks. Because of the nature of aluminum and the electrolytic solution that's in the batteries, it causes aluminum to make something called aluminum oxide. This aluminum oxide, if you've ever seen anodized aluminum, an Apple computer case, that's anodized aluminum. Basically what they do with this is they produce a thin layer of aluminum oxide. It's really resistant to everything. Dings, it's hard, not hardly any other chemical reacts with it or anything like that. But what happens in this process is this aluminum oxide gets into the electrolytic solution, and in addition to all the other properties of aluminum oxide, it doesn't conduct electricity. So the big drawback right now is as these batteries are in operation, they generally cut themselves off from the flow of electricity. The aluminum does. So as our project this year, one of the things that we're working on is to see what the kids can come up with in terms of reducing that problem in the battery. We've looked at adding some different chemical compounds to it. We've looked at a whole bunch of things. Right now, we're leaning toward a design solution. But anyway, that's the major drawback to these batteries. They're already in use by the military, and what their main application is, you know, you can go out and buy a pack of Duracell batteries. They'll sit on the shelf for 5 years, 6 years unused, and they will eventually go dead. An aluminum air battery has the potential to have an indefinite shelf life. In other words, it will last forever until you add an electrolyte to the aluminum. Once that process starts, it's hard to stop it. It puts out a large volume of electricity, but it goes continuously and it goes pretty fast. The military use these units right now in some prototypes for field radios and things like that. Basically what they do is they have one of these batteries. They take the battery into the field when they are running low. Their regular lithium-ion batteries are running low. They basically pop this emergency battery open, drop water in it, that activates the electrolyte, and they have backup electricity. So what we're looking at in this is my students, for this project, we're looking at taking several different possibilities in improving these batteries. We're going to measure these outcomes and hopefully create a small working prototype of one of these that we can improve on to the point where we can crawl onto a 3D printer or something like that and actually produce a prototype. Some of our drawbacks right now have been my students are pretty limited in CAD knowledge and things like that. But I would welcome you guys to contact me about this. This is something you will be hearing about in the future if you haven't already. And in addition to that, I think you'll see probably a lot of products in the future utilizing these batteries. And does anyone have any questions about this?